Hey folks, I'm Mr. Hartzler, and I wanted to talk to you a little bit about angles and the unit circle in this video. So I'm going to start sharing my screen with you, and we'll get rolling. All right, so you should see up there my whiteboard. I'm using a drawing tablet to do some of these things, and hopefully we can make some stuff happen here. So like I said, we're talking about angles and the unit circle. So I'm going to start off with angles. And you'll see me look down, and that's looking at my textbook and my notes right now too. So that's kind of why I'm looking back and forth here. But I want to point out positive angles and negative angles and what's called standard position. So I'm going to draw a little bit here. Ooh, that is crooked. Okay, let me straighten up my drawing tablet a little bit here. That's a little bit better, right? Okay, so let's say I have something that is over here, right there. So that's my line. This is in standard position. Let's even give this a coordinate point. So it's a -4, comma 4 square root of 3. That's my coordinate, or my coordinate points. One coordinate point. All right, and the initial side, we're always going to say, unless somebody for some reason says something else, it is this part of our x-axis right here. This is going to be our initial spot, and we're ending here in standard position. And we would call this edge here our terminal side or our ending side. And again, this one is going to be our initial side unless we specify otherwise. And theta would then be, let me switch colors up a little bit. Theta is going from our initial side to our terminal side. That is what theta is. Okay. Let's keep going because that is mostly obvious. Now, there's another way of measuring this, right? So here, this angle is going to be the positive version of this angle. I'm going to switch the color up again, and we're going to choose green. And this can also be represented as a negative angle. So if I start off at my initial side and I go clockwise, that is going to be a negative angle. Okay, so let's see, this one here is going to be a positive 120. Okay, so it's going to be a positive 120 degrees. The negative version of that is how much then? Well, a full circle is 360. Well, 360 minus that 120 is going to get me a 240. So this whole side here is 240 degrees, but it's a negative because we went down first from our this x-axis over here. That is important to note. So from here, if we go, or anywhere on here, if we're going clockwise, it's a negative answer. So I'm going to write clockwise, or CW. It is a negative angle. Now, if we're going counterclock, ooh, too many C's. One too many, there we go. Counterclockwise, then it is a positive angle. That is important to note, especially when we start getting into coterminal angles. So I'm going to clear this board right now. Let's save this and let's clear it. So let's get ourselves another drawing. I'm going to put up a coordinate grid here. Right there. Well, that's pretty straight. And right there. Cool. And let's put this on as red again. And let's do it. Let's do right here. And let's say that our angle is 45 degrees. So my angle is 45 degrees. The negative version of that angle, so that would be starting here and going all the way around this direction. That's going to be negative how much? Well, 360 minus the 45 piece is going to be 315. So it's a negative 315 degrees compared to this positive 45. But if I'm looking at that red 45, what if instead of just going and doing a little bloop, what if I went all the way around, then came back to this little edge? So that'd be 45 degrees plus a full loop around my circle, right? So that's now a 405 degree angle. Still a positive because I started at that x-axis and I went all the way around counterclockwise. So And it's now 405, and that is coterminal, or like terminal, right, is like ending, and co kind of meaning same. So they have the same ending, the 45 degrees and the 405. They end at the same spot. And the same works in the negative. So let me switch my color back to green. I have negative 315 degrees. Well, if I subtract another 360, right, that's now me going all the way around one full time negative. So I went all the way around once, negative wise, and then I went around another 315 degrees. So now this is going to be 5, 7, 675. And remember, this angle is negative because I went clockwise. So keep that in mind. All right, so we've talked about coterminal angles now. Let us keep going. And given the initial and terminal sides of a positive angle measure, a negative angle measure, and an angle measure greater than 360 of an angle below. Okay, so there's a couple of different things we talk about, and I'm going to save this screen and then I'm going to delete this. And we talk a lot in trigonometry about reference angles. So let me get another grid on here. And let's put up that, let's do this one over here. And it's a positive, let's say it's a 135 degree angle, okay? I'm not going to try and use sine, cosine, or tangent with 135. Instead, I want to try and find a reference angle. My reference angle is almost always going to be my x-axis, okay? So this in particular is a video for my Algebra 2 students, and pre-cal and calculus, things change up a little bit, sometimes in geometry, but for the most part, if I can, I want to reference my x-axis. It's going to be better for us that way. So I'm going to come straight down to my x-axis, my closest x-axis, or up to it, whatever it needs to work, to make a 90-degree angle. Now the question is going to be, what's this little angle in here between this terminal side and my closest x-axis? So keep in mind, it's 180 degrees all the way around the top half. If 135 is what's already taken up, well, then I've got to, steal from the 8 a little bit. So that's now 170 and a 10. 10 minus 5 is 5. 170 minus 130 is 40. Okay. So this little angle in here is 45 degrees. That's going to be my reference angle. Okay. So I'm not going to do sine of 135. Instead, I'm going to try and do sine of 45. Now, the problem with that, though, is I'm in a different location than what that 135 is, right? I'm in a different quadrant. So something that I want to speak about right here is that all students talk constantly. Some people say all students take calculus, but let's be honest, that's just not true always. But all students talk constantly is almost always true. It's true more often than when it's not true. And this means that all trig functions are positive. All trig functions positive. For the S, it just means sine is positive. Everything else is negative. T says that tangent is positive. All others are negative. And C is cosine is positive. All others are negative. So in this particular case, sine of 45, from my last video we kind of talked about, that should come from a memorized table. So sine of 45 is square root of 2 over 2. But now I need to determine, is it positive or is it negative? That's going to come from which quadrant I'm in. So I'm in the second quadrant. This goes 1, 2, 3, and 4. So I'm in the second quadrant, all students. So sine is positive. So I got to throw a little plus there. Now let's do cosine of this same thing. So cosine of 45 degrees. Keep in mind, this is 135 if I'm using my reference angle of 45, okay? Because it's a lot harder to make a triangle with the weird 135 in it, right? So instead, I'm going to make a triangle that's over here, this 45-degree triangle. Cosine of 45 is still square root of 2 over 2, But remember, it's in that second quadrant. It's over here. Cosine is negative there. All right, so I'm going to keep going a little bit because I think that's going to be a little bit more helpful if we get a couple more things in here. So let's save this one. Let's clear this one. All right, so we've talked about initial side, terminal side. We've talked about coterminal angles. So those are angles that end at the same place, right? So that's 15 degrees and 375 degrees because it went around one time, then another 15 degrees. And I could keep adding 360 to that and keep getting more and more coterminal angles or same ending angles. But let's go on and let's look at 210 degrees. So I come all the way around here to this spot, and I've moved around 210 degrees. Now, if I were to build a triangle off of this, again, I want to go to my nearest x-axis. So I'm going to come straight up in this case. Make a little right triangle there. What is this part, just this little chunk here, of this triangle? Well, it's 180 over to this line. How much more do I have to go? 30 degrees. Ooh, that's nice, right? Because that means this is a 30, 60, 90 triangle. So that's kind of cute. So 210 degrees, I'm going to use my reference angle of 30 degrees. Then I have to check whether it's positive or negative. So let's look at this here. So sine of 210 degrees, that's going to be the same number as sine of 30 degrees, okay? Whether it's 30-degree angle here, so that's actually, I'm gonna draw that on here. All right, there. So this is another 30 degrees. It's a right triangle. Both of these triangles, hopefully we understand that they're the same size, okay? Assuming this leg here is the same length, but they're same proportionally. They're similar triangles. So that means that their number here, their length of their opposite leg over their hypotenuse, right? So SOH, so opposite ratio over hypotenuse, that's going to be the same for both of these triangles. However, the sine of 30 is going to be positive. It always will be, because in that first quadrant, all trig functions are positive. 210 though, that is over in the third quadrant, and all students talk constantly. In the third quadrant, tangent is positive, so everything else is negative. So I've got to make this a negative sine of 30 degrees. So sine of 210 degrees is going to equal negative of sine 30. So let us delete that negative real quick. Sine 210 equals sine of 30, number-wise, if I disregard positives and negatives. But if I start to pay attention to positives and negatives, sine 30 is going to be negative if it has to equal 210. And that just has to do with the quadrant I'm located in. All right. Hopefully that's helpful. Let's do cosine now. So cosine of 210 is going to equal cosine of 30, okay? Same triangles, okay? That's all that's happening here. I have the same kind of triangle. But because I'm in that third quadrant, I have to account for things being negative, right? This coordinate point would have a negative x and a negative y coordinate point. That's why cosine 30 has to have a negative in front of it. That's why sine 30 has to have a negative in front of it. I hope that helps a little bit. Some of this honestly just comes with practice and using it a little bit more. And hopefully in class I can discuss this a little bit more. I know for my students right now we're doing some distance learning, but all right, let's keep going here. We've talked a little bit about reference angles, and that starts to lend towards the unit circle. And the unit circle is literally a circle. Well, it's a terrible circle. You know what? I might be able to use and make an actual circle. Oh, there's a circle. Oh, I can move it. Cool. All right. So I have my unit circle there. This is my origin, We should hopefully remember that. My x-axis, my y-axis. Cool. Let us put a little triangle inside of this. So that means I'm coming up to right here, and then it'd be coming straight down and make a 90-degree angle, and then back to the center. So for the unit circle, we are going to assume that the radius is equal to 1. Just 1 unit. Doesn't really matter what it is. So 1 unit. So that means my hypotenuse for whatever triangle I'm going to put in here is 1. That's kind of nice. Because this coordinate point, we'll call it just x, y right now. So that means the height of this, I would label as y, and the width of this triangle, I would label as x. So let's now find out what sine is. Sine of theta. Here's theta right there. Okay. Sine is opposite over hypotenuse. So the opposite leg is y, and the hypotenuse is 1. So this is where sine theta straight up equals y. That's kind of cool. It's kind of nice. Kind of helpful. Let's look at cosine. See what this ends up being. Cosine is adjacent over hypotenuse, so we get an x over 1, which just gets us x. Okay. So I'm going to adjust this triangle a little bit, right? The numbers here. So my coordinate point is not just x, y, but it's actually cosine of my angle, comma sine of my angle. So I can use now trig functions to find out where a coordinate point is if I only know the angle. That's really helpful. I mean, you might not see it yet, but in real life, that's actually pretty helpful. So let's do that for a particular example. Let us clear this screen off a little bit. So here is this, and there is that. We're dealing with a unit circle, so we'll say that all of these radii are going to be 1. And let's come up and let's say that we have a 45-degree angle here. And I want to find out what this coordinate point is. So what is this coordinate point? I can find that now. So I have my x part of this is going to come from cosine of my angle. My angle in this case is 45. Again, we're assuming that this is 1, our radius. Cosine of 45, for my last video, I told you should memorize this, but it is square root of 2 over 2. So that's my x coordinate. And my y coordinate comes from sine, so sine 45, also equals square root of 2 over 2. So that's kind of cute here. So I just found this point in space only knowing its straight length, so as the crow flies, from my origin, and the angle. That can be really helpful for a couple of reasons. Sometimes it's easier to find an angle between two things and the length from one spot to another instead of like both of those legs, right? Instead of trying to find my x coordinate and my y coordinate. So that's taking two potentially really long measurements. Let's say I'm surveying, I can measure the angle between a point of reference and my particular point. Okay, so that would be that 45-degree angle in this case. Or on a baseball field, it's my angle from first plate to third. And then I just need to know how far is it from here straight up to third. That's it. Instead of trying to take a tape measure going across both things, I can just know the angle between them and the length of the one piece. So that can be really helpful. All right. All right. I'm going to save this and clear this again. And I'm actually going to stop sharing my screen for a minute because I want to talk to you. So degrees and radians, two very separate things, but they measure the same stuff. So I could measure the distance between my hands. I could measure in inches or feet or meters or centimeters or yards. I could do it in all kinds of different measuring tools. But now let's say I'm measuring the angle between my arms, okay? Well, actually, I'll do it like this. The angle between my hand and my shoulder, right? So this angle in here. I could do that in degrees. A lot of us are familiar with degrees, right? You do a 180, you do a 720 or 360. But there's a better way of doing that. It doesn't seem better to us, especially early on, but it will eventually be a little bit easier and better. So instead of an arbitrary number of 360 degrees, if I were to go all the way around, we're going to pick a pretty solid number, a pretty rock solid steady number. So let's share this. So this number is going to be based on radians. Okay, that's our new unit. Instead of, where's my cursor here? Instead of 360 degrees, we're going to equal 2 pi radians. Now this is for a particular reason. So we talked about that unit circle earlier. Well, its radius is 1. And I can always scale that up or scale that down, but 1 works, right? Either 1 meter or 1 yard or 1 gajillion miles. It doesn't really matter. But let's say that it's just 1 right now with no unit on it. What's the circumference of this circle? Circumference comes from 2 times my radius times pi. It's also diameter times pi, but I don't know the diameter, right? So let's use it based on a radius. And our radius being 1, 2 times 1 times pi, so 2 pi. That's my circumference. That's all the way around this circle is going to be 2 pi. We're going to label that in radians, kind of based off of its radius, right? So now if I want just half of this circle, so maybe I cut it in half here, from this chunk all the way over to this chunk is going to be how many radians? Well, it's going to be pi radians. If I were to cut that piece in half from my initial side to my terminal side of here, well, that's going to be cut in half again, and that's going to be 90 degrees or pi over 2, right? Cut my pi in half. The pi like 3.14, not the delicious kind. All right, I'm going to delete this little chunk here and let us, okay, and all right, and let us now draw, and I'm going to change back to black here. So all the way up to here, this is going to be pi over 2 radians, and I'm starting here. So I go over to 180 degrees, which equals pi radians. Down here, it's 270 degrees, or 3 pi over 2 radians. Complete my circle, and I'm now at 2 pi radians, or 360 degrees. Again, it doesn't seem incredibly helpful, but just think about this like a unit conversion, right? It's just measuring two different, or the same thing in two different measurements. So like miles and kilometers, because I don't know, math people like being different. So, all right, let's talk about how to go from one to the other. So let us clear this. And let's say I have 30 degrees. I need to get that into radians, which you don't actually write unit for. Like I wouldn't write the word radians. I would just leave a number, which is kind of cool too. It contributes, or it is part of the reason why math people are so lazy, right? So what do I have to multiply by to convert from degrees into radians? So I want degrees to be on bottom, and I want radians to be on top. And I had already told you that 360 degrees equals 2 pi radians. So you can use this ratio. So in this case, I would have 2 pi on top and 360 on bottom. But we can be a little bit more efficient. So those simplify a little bit, right? I can divide both of these things by 2. So now 180 degrees equals pi radians. This we would call an equivalency relationship, or an equivalency relation. So now I could say pi radians over 180 degrees. Pi radians over 180 degrees. My degrees symbol will cancel. I'm no longer in degrees. I'm now in radians. And 30 pi over 180. This simplifies a little bit. So first, I'm going to knock off these zeros. So now 3 pi over 18. But now 3 goes into 18 6 times. So this is pi over 6. There we are. So the nice thing is, if I have my measurement, right, first chunk here, first 30 degrees is pi over 6. My next 30 degrees, so now I'm up to 60. This is 2 pi over 6, or pi over 3. All the way up to this middle would be 3 pi over 6, or pi over 2, right? I'm just simplifying those fractions at this point. Oh, I feel a sneeze coming on. Hopefully it passes. But let's skip to here. I'm 30 degrees short of my x-axis on this side. Keep in mind, this is a full pi radians, or 6 pi over 6. I'm 30 degrees short, or I'm a pi over 6 short. So this angle over to here is a pi over 3. So this whole chunk is 5 pi over 6. This one should have been over 6. Sorry. So I'm going to write it down below. All the way over to here, I know this little chunk is a pi over 6 because it's only 30 degrees as my reference angle. So I know the big angle is going to be 5 pi over 6. So that's one of the reasons that radians can be helpful once you get to manipulate them a little bit, is I can count backwards a little bit easier with radians than I can with degrees. All right, let us keep going a little bit. I know a lot of this is moving kind of quick, but through some examples, I think once you get working on those, I think that'll be helpful for you. So, let's see here. The next one. All right, we've talked about this. Okay. All right. So let's talk about arc length a little bit. So the length of an arc, so our arc length is going to equal our angle times our radius, but this is only true if theta is in radians. Just keep that in mind. If it's not in radians, you have to get it into radians first. So let's say I'm using pi over 4. So my arc length is pi over 4. If you have a hard time with that, let's do a quick conversion. I'm going to do that over on the right here. So pi over 4, converting it into degrees, I need degrees on top, or 180, over pi radians. Pi's are going to cancel, and I'm left with 180 over 4. So that is 45 degrees. So I have a 45 degree angle, or pi over 4 here, radians. And I need to find out the arc length. So that would be this chunk here, from initial side to terminal side. How long is this arc? So I'm going to take my angle, which is pi over 4, and I'm going to multiply by my radius. Let's say for this instance, for this case, it's a radius of 10 feet. Multiply by 10 feet, and I end up with, that is 10 pi over 4, again in feet, which I can simplify this a little bit, right? So it's going to be 5 pi over 2 feet. And I do not have a little calculator, or calculadora in Spanish. I don't have a calculator on me, so I'm not going to figure out what this exactly is, but that's, 15.7-ish divided by 2. So that would be not 8, but 7 point something. Okay, 7 point something feet is how long that little swing would be, that little arc right there, that red arc. And if you didn't have this in radians, so let's say we had it in degrees, let's discuss what that would look like. All right, let's erase. Okay. So now treat it like it's in degrees. So I have 45 degrees. And I am going to still have to multiply this by the radius. But I have to first, all right, here, we'll go back a little bit. Let me erase this again. How do I find the circumference of the entire circle? So circumference is going to be 2 times my radius times pi. So I switched the order up there, but 2 times pi times my radius is going to be my circumference. But I don't want the circumference of the whole circle, right? I just want a fraction of the circle. So I'm going to multiply this. My arc length, if I'm looking at degrees, is going to be 2 pi r times, what's the fraction of this arc going to be? So it's going to be 45 degrees out of an entire circle, which is 360. And then I would simplify this and plug in my 10 again. So 2 times pi, 10 feet for my radius, times 45 degrees for this particular piece out of 360 degrees for my whole circle. So that is finding arc length through radians and through degrees. Hopefully that was not too confusing. All right, let's see. What else? That's pretty much it right there. Boom. That's sweet. Okay. So I hope that was helpful for you people, for everybody out there. I'm going to save this one and we're going to clear it. I'm going to stop this share. Okay. So we've talked in this one about initial sides, about terminal sides, coterminal angles, so angles that mean the same thing. We have also talked about converting between degrees and radians. Try and get yourself familiar with using radians. I prefer using radians, especially in class. If you were one of my students and we were in class right now, I would actually not even allow you to tell me anything in degrees. We would only do things in radians, mostly because it is just stronger. And if you start to pick up on some of the patterns, it can become a lot easier to maybe count backwards from an edge instead of always having to count up to it. And then we talked about arc length a little bit using both degrees and radians, and that's a big part of this. So the last little chunk that I recommend for all of you is to go through and label a unit circle. So let me share my screen with you one more time here. So if I had a little graph here, on a Cartesian plane, so this first chunk is 30 degrees. You should also then label this as pi over 6. And then you have 45 degrees, right? Well, that's the same as pi over 4. And then you keep going, and this is 60 degrees, and that's pi over 3. And that pattern repeats, right? So over here, 30-degree reference angle, this is another pi over 6. And this other 45 is another pi over 4. This one just happens to be 3 pi over 4, right? And 60 degrees, so this is another pi over 3, but my full, or as a reference angle, but my full angle is going to be 2 pi over 3. This middle one is a pi over 2. And we talked in the beginning a little bit about all of these coordinate points being an x comma y, and it's a cosine comma sine. So this is going to be cosine 30 degrees comma sine 30 degrees. Well, I know what those numbers are, right? So that's going to be cosine of square root of 3 over 2, and sine of 30 is 1/2. So I can go through this entire unit circle. You can find templates online, but this next one, cosine of 45, is a square root of 2 over 2. Sine of 45 is square root of 2 over 2. They're the same thing there. All right, but then I come up here to my 60-degree angle, and cosine of 60 is 1/2, and sine 60 is square root 3 over 2. So again, my x coordinate, you'll start to notice, right? Cosine, my x, it gets shorter or smaller each time here. It goes from square root of 3 over 2, square root of 2 over 2 to 1/2. While sine, it's growing taller, right? I'm starting to raise that bar up, so it's getting farther and farther away. So it starts off being half up, then square root of 2 over 2 away from the x-axis, and then square root of 3 over 2 from the x-axis. And right up here, all the way up on my y-axis here, it's going to be 0, comma 1. Just like on my x-axis here, it's 1, comma 0. All right. So again, hopefully that was helpful for you. And if you have questions, please leave that in the comments below. And as we go through all of this, please ask me questions. Email me if you're one of my students and you need to know something, or if you need clarification Or maybe this video was just bad and I have to make a new one because I didn't explain things thoroughly enough. Please let me know that so that I can help you better. And if you like this video, please click the like button, subscribe to the channel if you want to see more stuff like this, and just so I can get my subs up. Come on now, folks. How am I going to get rich unless you subscribe? All right, have a great day, everybody. I wish you well. Do math carefully and with enthusiasm. Bye, everybody.